Hey everybody, we're here today to start chapter 3, which we're going to begin talking about fluid dynamics or fluids in motion. And we're specifically going to start talking about the Bernoulli equation, which is a very famous relationship with wide range of applicability and some very important limitations. So in this vodcast, we're going to cover sections 3.1 through 3.3. We're going to talk about the development of the Bernoulli equation, and we're also going to define some terms. There are some specific ideas that we need to work with and be familiar with. So I'm going to start by putting a couple of these ideas on the document cam. The first is when we talk about fluid dynamics, we talk about fluids in motion. In chapters 1 and 2, we talked about fluid statics or fluid mechanics. So now we're starting to get things to move. And one of the things that we need to remember is that we view fluid as a continuum. Which means that we do not look at the whole thing. Like if you have a lake full of fluid or a river full of fluid or a pipe full of fluid, you really can't look at the whole thing. So we have to look at ways to observe and quantify the fluid and then extrapolate or integrate that to cover the whole body. So one way that we do this is by thinking about fluid as moving along what is called a streamline. Now later on we'll also talk about streak lines and path lines, but for now let's just talk about streamlines. In steady flow, these three things are the same, but always a streamline is as a particle of fluid. So we can talk about that particle as being a particular molecule or as a differential element. But as each particle slides along its path, we call the velocity vector everywhere. Well, we know that the velocity vector is going to be everywhere tangent, but the lines that are tangent to the velocity vectors are streamlines. But so let's go ahead and write this out completely. As a particle of fluid slides along its path, the velocity vector of that particle is everywhere tangent. So if you think about it backward, connecting the tangents of the velocity vectors as that fluid moves is called a streamline. All right. So if we have a fluid, for example, moving through some two-dimensional situation, let's call our coordinate axes x and z. And if we have flow in the xz plane, we can describe a particular particle of fluid, whether we call it a dot or a little differential element of some sort, as moving along a particular path, right? And everywhere along that path, the velocity vector is perpendicular to that path. So this is a streamline, and that direction is called sub s. So we would call the velocity, if you think about it, there's two components of velocity, but we have a v sub s, which is the velocity along the streamline. And we also have v sub n, which is the velocity normal or perpendicular to the streamline, or we could say across streamlines. So if you consider this, what we've talked about so far is one particle. But if we had a pipe full of fluid or a tube full of fluid or any sort of a vessel at all full of fluid, we're going to have different streamlines because that particle moves this way and this particle moves this way. So we're going to have the direction along the streamline, and we're going to have the direction perpendicular to the streamline as well. Now, what happens here if you think about this? Do you remember from physics or dynamics when we talked about radial coordinates? We talked about a radius of curvature of a path that an object took, and we had a velocity along that path, and we also had a velocity normal to that path. Okay? And we recognize from Newton's second law, force equals mass times acceleration, that when we break it up into xy or xy and z components, that we have a force in the x direction, acceleration in the x direction, and so forth. But for radial, or normal tangential, we could say the summation of forces tangential is equal to mass times acceleration tangential. Let's get a vector. And similarly, the normal force is equal to mass times acceleration in the normal direction. All right. Now, if you also recall, this acceleration is the change in speed. So a dv dt term. But this acceleration is not a change in speed, where speed is the value or the magnitude of the velocity vector, but acceleration normal represents a change in direction. And instantaneously, that was equal to v squared over r, where v is the velocity of the particle, or excuse me, the speed, the magnitude of the velocity of the particle, and r is equal to the radius of curvature. Now, we can also say, in this case, that the acceleration along the streamline is equal to the velocity times dv ds, which is another expression of this. Now, this, once again, this comes from dynamics or physics, but remember, velocity is dx dt, or in this case, if we're along a streamline, ds dt. So if we multiply that by dv ds, the ds's cancel out, and we get dv dt. So that's the equivalency of this and this. All right. Now, in your textbook, they go through a mathematical process of starting with Newton's second law and arriving at an equation of motion for fluids along a streamline and perpendicular to a streamline. But there's a couple of definitions we need before we can start talking about that math. One of them is, if you remember from chapter 1, we talked about viscosity. Now, we talked about two types of viscosity, dynamic viscosity and kinematic viscosity, one of which has the density or specific weight of a fluid involved in the calculation, and the other does not. But viscosity in general represents a resistance to shear. And it turns out that for fluids in motion, the viscosity is a big deal, and we have to take into account at every turn. However, there are places in the fluid where the viscosity effects become negligible, and that is referred to as inviscid, meaning viscosity effects are negligible. So it turns out that there are places in a fluid flow where the viscous effects need to be taken into account and places where they do not need to be taken into account. Hang on a second. There we go. I have to label that page so I didn't get it mixed up. All right, so what I mean by that is if you have fluid, for example, flowing through a tube or a pipe, looks like this. This just represents one end of the tube. and this is the other end of the tube. And they're both open, and you have fluid moving through the pipe in this way. When we talk about the velocity of the fluid, it turns out that we're really talking about an average velocity, and that the velocity of the fluid here at the wall may be significantly different than the velocity here. And what tends to happen is you get a nosing out or parabolic shape of fluid movement. So if you started with a flat profile of fluid here, that it will nose out as it goes through this tube. At the walls, near the walls, and near, we'll have to quantify later, but near the walls of the pipe or the tube, the viscous effects are very important. But toward the center of the tube, it's often the case that the viscosity is not important, and that we actually can approximate the fluid flow in that region as inviscid. So away from the walls of the tube, or the walls of the conduit, to be more general, inviscid flow may occur. It's not always the case, but it's common. Right. So how far away from the walls of the tube, and to what degree, and how much of the fluid we can omit, and what that nosing out profile looks like, those are all characteristic upon the flow regime itself. But that's when we talk about viscosity and inviscid flow, those are sort of the ideas that we come up with. All right, so as we move along then to section 3.2, we are going to talk about Newton's second law of motion, F equals ma, along a streamline. And basically, along a streamline, we're going to have, let me draw this again. Let me draw an x, z coordinate system and a streamline. And if we think about the forces acting on this particle of fluid, first of all, we know that weight is always pointed vertically downward. So if we knew an angle, for example, this looks like physics, I think. If this angle is theta, we know that we have a component of weight. And since we're talking about a differential element, we call that the weight of that differential particle dW. Well, if we just want the component along the streamline, because we want to get the force that's just either moving it down or pulling it back on the streamline, we could say that is equal to negative, because of the sign convention down being negative, dW times the sine of theta. And the del W, I said dW, but I really meant dW, could be approximated. Remember, since this is weight, we could call that gamma times the differential volume. Okay, and once again, times the sine of theta. Right. Now it's important to note, we've gone over this before, but velocity, which I represent with an arrow over it, your book just uses a straight V, or volume, even though they're both V's, are very different. So your authors use a slash through the V in order to differentiate it from velocity. We also have a pressure differential from this side to this side, and we can think about that as being along a streamline, as being, if there's a difference in pressure from here to here, and this is the center, we can sort of approximate that by a one-term Taylor expansion. And we did this back in chapter 1 also. We didn't really talk too much about it. But we can say that it's equal to dPdS, which would be the pressure gradient along the streamline, times del S over 2. All right? And that, you can think of that as being in the middle, averaging in the middle, or you can think of it as a first-term Taylor expansion. All right, so if we continue thinking about that, we can say that there's the sum of the forces along the streamline, defining our vector direction, is going to equal the differential mass times the acceleration along the streamline. And we can plug in those terms and work with it a little bit, but basically we know that this is going to be the weight and the pressure terms from up here. And so we could pull that together and just write it as negative gamma times the sine of theta minus del P del S times the dV term. Okay, because we have that in both of those terms. And gamma, let me just check my units, PS, yep, so that's going to give us a del force. All right, so the way I have it written, my signs are all correct as well, just making sure I had everything working properly. So if we then want to talk about a force over a volume term, which would be force over V, we can divide that out and come up with negative gamma sine theta minus del P del S equals, this is the mass times acceleration, once again divided by volume, which is a rho V dV ds, remembering the derivation for the dV ds. Let me pull this up here again for acceleration. Acceleration equals dV ds coming from this term. All right. And we can also then refer to that as rho times acceleration along the streamline. So this is more or less the finished value of the equation that equates a pressure gradient along a streamline to a component of the weight and the acceleration of that particle of fluid. All right, so if you're looking for a pressure, a differential pressure or a pressure gradient, then you can, if you have a relationship of volume as of velocity as a function of position, and you know density or gamma, and remember gamma equals density times gravity, right? So you have that relationship to use as well. You can find out some interesting things about the way a fluid behaves along a streamline using that question. And one of the reasons that you would want to do this is because it's important to remember that the net pressure force on a particle is determined by the pressure gradient. All right, so those are some ideas. In your textbook on example 3.1, they do this where you have a velocity as a function of an initial velocity, which is a constant, of course, and a position in x. So you can see that this, if it's given as an x, the streamline is directed along the x, so dV dx would be equal to dV ds in that particular case, and you can work that problem through and see where you're going to go with that. All right. Now, as we work through this a little bit more, I'm going to skip ahead to 3.3 and take a look at the F equals ma across streamlines. And then I'm going to come back and give you Bernoulli's equation, which really is discussed both in section 3.2 and 3.3. So basically, starting out the same way, we know that the summation of forces, we're talking about a differential element, only this time we want to go normal or perpendicular to the streamline, is going to equal mass, which is that differential element m, times the acceleration, but remember we're talking about v squared over r, and your authors use a scrolly r here, a cursive r, but that's just a little hard for me to draw, so I'd like to leave it as this. Well, we know that del m is going to be rho times del v for volume times v squared velocity over r. And then we can think about what forces act across the streamlines. Well, what are the forces that are going to act? We're going to have some sort of a weight. And in other words, if we use the same sign convention, last time it was weight sine theta along the streamline, so this is going to be weight cosine theta, using the same convention. And then we've got that pressure deal as well. I guess I should call these negative because we're still going down, being negative. Let's just call it del P. And last time it was del S, so this time it will be del N. So we're going normal or perpendicular. And that's going to equal the negative or gamma cosine theta, using the same pictures we have where theta is that angle. Only now we're going this way, right? So we have gamma times the cosine of theta minus del P del N, pressure gradient perpendicular to the streamline, and then to get our units correct into units of force, we need the differential volume. Okay. All right, so one consequence of this is because we have weight and we have pressure, and from a cardinal coordinate system or Cartesian coordinate system, those directions are changing, right? Weight and pressure can produce curved streamlines. And that's why we have to take into account that radius of curvature and treat it like radial coordinates. Just checking my work here. All right, so if we have pressure only, so in other words, what if we had a horizontal direction if our streamline was vertical, for example, and so our perpendicular direction would be horizontal. There's no component of weight in that direction, is there? Well, that would be one case where we would have del P del R, that's the radius of curvature, is going to equal rho v squared over r. In other words, this is the equivalent of mass times acceleration, and this is the force. Now, the units are a little bit different here, but we need to just make sure that we get the units. Remember, if we have a pressure term, a pressure is in dimensions of force per area, which is force per length squared, and r is going to be in length. So if I take this and I divide it by this, I'm going to have force per length to the third, which is really a force per volume term, isn't it? Okay. So just bringing that up. And the same over here. Density is in mass per volume, which is length to the third. Velocity is in length per time. And since it's squared, we're going to be time like that. And then the radius is going to be in units of length. Okay. So then we're going to have to work this out. Just to be clear on this, let's go ahead and finish. Mass, we have length squared on the top, length 4 on the bottom. So that's length squared times squared. Okay. What happens with mass? Well, from Newton's second law, force is equal to mass times acceleration, or the dimensions of mass times length per time squared equals force. So if we need to convert between the two, we can say that force, let's just go ahead and plug it in this way, force times squared per length equals mass. So we would say force time squared per length, Substitute for that. Length squared, time squared. And the time squared cancels out. We have force per length to the third, force per length to the third. So we have dimensional homogeneity on those units. All right. Now, let's get to the idea of the Bernoulli equation. All right. So going back, we're going to talk about the Bernoulli equation in two different ways. We're going to talk along a streamline. And across a streamline. So this is the S direction, and this is the N direction. All right. Now, so if we go back and we take a look, there is a form of the Bernoulli equation along the streamline that's written like this. The integral of dp over rho plus 1/2 v squared plus g times z is equal to a constant. All right. I'll come back to that in just a minute with the implications and a simplifying assumption. Normal to a streamline, it's written a little bit differently, but you'll see some similarities. We get pressure plus rho times the integral of v squared over r dn plus yz is equal to a constant. All right, now as you can see, first of all, this one looks a little bit more complicated to use, doesn't it? But it takes into account the difference in the acceleration terms, and we have something equal to a constant in both cases. Now, I want to change something up just a little bit, because this term, let me go back one. So this is equation, this is form 2. I want to go back to form 1. We're going to have dp over rho. I kind of want it to look like this. Plus v squared over r dn. So that's similar to this. Plus gz equals a constant. Okay. And this, of course, your book has it written as y, but it's actually a z. So I want to make this note. That's on page 111 of your textbook. Equation 312. This should be g, not y. All right? So it's just the gravitational constant, 32.2 feet per second squared, or 9.8 meters per second squared. All right, so we have equation in form 1, equation in form 2. And then here along the streamline, which is really the one that we'll use more often, we'll take a look at this equation as well. Now, we can simplify this if the pressure is constant. This is actually if P is constant. Excuse me, if rho is constant. So in other words, if it's incompressible. Okay, because what happens if rho is, if it's incompressible, rho comes out, and this just integrates to delta P over rho. All right, so same here. If rho is constant, same thing happens. And the Bernoulli equation in that case will simplify to P plus 1/2 rho v squared plus gamma times z is equal to a constant. So what have I done? Well, if you think about this, we know that gamma is equal to rho times g. So in other words, I've multiplied through this equation by rho, haven't I? I've multiplied this by rho, and since it's constant, it just goes to P. Multiplied this by rho, it appears here. Multiplied this by rho, and it appears here. All right, so the consequence of the Bernoulli equation is that at any point along a streamline, let's just talk about this form. At any point along a streamline, this equation will hold true. So we could say if rho is constant for a fluid in motion, along a streamline, we could say P1 plus 1/2 rho, which we're assuming to be constant, not assuming, we have to have it be constant, V1 squared plus GZ1 equals the pressure at some other point 2 plus 1/2 rho V2 squared plus GZ2. All right, so this has enormous consequences. What we're really talking about is the fact that pressure and velocity and position are all basically forms of energy or force, or there is a force times a distance. In this case, it's a force divided by a distance, so I have these units written. But basically, if we have pressure, velocity, and position, height, we can trade them off into other forms of water, or other forms of energy. That's why, for example, if you have water flowing over a waterfall, it will tend to be faster here than it will here because you've traded in potential energy for kinetic energy. So this is basically a kinetic energy term, and this is basically potential energy term. But when we have a fluid moving, especially it's in an open system, the pressure doesn't change. But when we have a conduit, like if you have a pipe like this, for example, there's going to be pressure differentials possible from here to here. Where it's open to the outside, we know from our manometry studies that that won't be different at those points. But if you can change the pressure, then you can trade off some pressure energy for potential energy or kinetic energy as well. Now, here's another consequence of this equation, the Bernoulli equation, along a streamline that I'd like to show you. If I rewrite this, and if I consider then the fact, if I divide each term by G, and since G is a constant, that will also be a constant, I can write this equation as P over G plus rho V squared over 2G plus Z equals a constant. Well, if you look at this, Z, that's in dimensions of length. And if you run the numbers, you'll find that these two terms are also in dimensions of length. So what we can relate to is we can report fluid energy in dimensions of length, and specifically its height. So what that tells us is that in some way the position of a fluid and the energy of the fluid are interchangeable and are inextricably linked with each other. So it's kind of an interesting consequence. Whenever you use the Bernoulli equation, you want to be very, very careful to keep your units straight. You also want to be sure that in order to use it in this form, you have to remember that it has to be an incompressible fluid. If the fluid is compressible, you have to keep it, excuse me, I want to come up here, in this form. All right, so to finish this off, I'd like to work a problem for you. And the problem that I'm going to do is a pressure gradient problem. It's problem 3.6 in your textbook. So I'm going to go over here to the problem set in the text. And 3.6 is on page 145. And it asks us what pressure gradient along the streamline, okay, so we know that's dPds, right? What pressure gradient along the streamline is required to accelerate water upward in a vertical pipe. So here's my pipe, and I want it to accelerate upward. Since the pipe is vertical, that is the acceleration along the streamline, isn't it? Because that's the direction of the fluid, that the fluid particles are moving. let's see, I've got to read, at a rate of 30 feet per second squared. Okay, and what is the answer if the flow is downward? All right, well, going back to my original equation, let me find it here from section 3.2, where we started with Newton's law, and we looked at this. Okay, we don't have to use this form because we actually have acceleration along the streamline is 30 feet per second. Density of the fluid, we know that it's water. This is what we're solving for, and this is the weight term. Once again, we know gamma for water, and we can determine the sine of the angle, sine of theta, because it's the difference between it's the difference between this and this. So theta is 90 degrees for upflow, right? Which is just a way of saying that all of the weight is acting against it. And theta is minus 90 degrees for downflow. Just saying that all of the weight is acting in the same direction as the acceleration. All right, so let's go ahead and set up the equation then. We know that minus gamma sine theta, just rewriting that equation from before, minus del P del S, which is what I'm looking for, is equal to rho v dv ds. But v dvs is acceleration along a streamline, right? So it looks like that. And then we have minus gamma sine theta minus dpds, and then I want to solve for dpds. So I get dpds, which is that pressure gradient, is going to equal minus gamma sine theta minus rho as. Right. All right, so for the flow going up, we get, let's see, let's go back here. For the flow going up, we're going to have this be minus, so it's minus gamma of water, which is 62.4 pounds per cubic foot, times the sine of theta, which is 1, minus rho of water, which is 1.94 slugs per cubic foot, times the acceleration, 30 feet per second squared. My sign conventions look good. All right, so that's equal to dpds. All right, so then this is going to be a negative, and this is going to be a negative, which makes sense because the pressure gradient should be higher if we're going up because everything is working against the force of gravity. So if I take 62.4 and multiply by 1, that's really hard, 62.4 minus 1.94 times 30, and we can resolve the units on that as well. Clear, clear. 1.94 times 30, and that number is 58.2, and that those two together are going to be dpds. So my number then is plus 62.4 negative 120.6 equals dpds. Now, the good news is we have almost all of our work done. I would just have a sign change for if it's moving downward, but we need to make sure that our units are correct. 62.4 is going to be in pounds per cubic foot. And this, we have slug feet per second squared per foot cubed. Now I wrote this slug foot per second squared because I know that this is a pound of force. Okay, so what that tells me is this is in pounds per cubic foot, and this is also in pounds per cubic foot. Pounds of force per cubic foot. All right. Now, there's a little something funny about this number. The answer is, well, it's not funny, but I just want to point something out about what's going on in your textbook. Pressure needs to be measured in pounds of force per feet squared, which is called a PSF. Okay, so we could report this as minus 120.6 PSF per foot. And that is the correct unit for a pressure gradient. This is the correct number, and it's the correct value. The answer that your authors give, they have the correct process, the correct answer, but then they call this a PSI per foot, and that is not correct. Okay, because if we had done that, we would have had to go PSF, or pounds per foot squared, times 1 foot squared per 144 inches squared to get a PSI per foot, and so this number would actually be divided by 144 in order to be correctly reported in PSI per foot. So just making a point. Okay. Now, if we're going down, we still have sort of the same ideas, except for this is going to be a negative one, so this value is going to be positive. So it's going to be plus 62.4 minus 58.2, and that's going to be my DPDS. Once again, it will be in PSF per foot. So here we have 62.4 minus 58.2, and that value is 4.2. And it is positive because this is bigger than this, PSF per foot. All right, so if I wanted to report this in PSI per foot, I would divide both of those numbers by 12 times 12, 144. This number would be 0.029 PSI per foot, and this number, 120.6 divided by 144, is 0.8375 PSI per foot. Right. So that gives you an idea of how to work with the units and how to get from point A to point B, starting with pressure gradients. So that's a fundamental concept of the Bernoulli equation. So that's the end of our discussion for sections 3.1 through 3.3. We'll come back and we'll do 3.4 and 3.5.